All right, hello everyone. So this is my intake demonstration. So today we're just going to be going through and designing a 2020 intake mechanism. Just as kind of an overview of the design process and kind of what we go through during the season while making actual mechanisms. So this is kind of the modeling process. So we'll start out by creating a set of sketches to represent the mechanism. And then we'll use those sketches to create plates and other miscellaneous custom components, and then we'll assemble it. So a relatively straightforward process, though each of those steps is obviously pretty complicated. So today we're going to be designing this mechanism. This is 254's intake from the 2020 FRC game. Basically, you had 7-inch power cells, they were called, and they rolled in from the front, and then they would get pulled up and over the bumper and into the robot. And then notably, it's on a 4-bar, so it can pivot up to get into frame for starting every match. And so they use a pneumatic for that. Depending on our time, we might or might not look at that today. Yeah, so let's get into it. So I'm going to start out by making a sketch on the right plane. And so basically what I'm going to do is I'm going to start out by creating a representation of the bumper. And the reason for that is just so that way we have an idea of what we're rolling the ball up and over. So this is kind of important for understanding the representation. So I'm going to make it 5 inches tall, and let me see here, 2.5 plus a 1/4 inch plywood is what the bumper is backed by. It's 5 inches tall, and then off the ground it will be, we'll go off the origin. We'll do 2.2 inches is fine. I think that's the minimum clearance. So we're going to assume that the bumper is lower, which is actually better for intakes. And then I'm going to use a sketch fillet to actually round it off. So I'll choose my 2 point, I'll click it, oh boy. And then our radius for the pool noodles, each pool noodle is 2.5 inches. So we'll do 2.5 divided by 2 for the radius. So that is our bumper. So that's sketch 1. Why do I have 2 sketches? Okay. All right, yeah, so I'm going to start a new sketch. I could keep adding on to that sketch. But basically the major benefit of starting a new sketch is it keeps things nice and simple. You'll notice that all the dimensions and things from that sketch disappeared because we're no longer working on it, right? So now I'm going to make 3 circles representing the rollers, right? So each circle is representing a roller position. And then you can see our bumper, which we've already drawn. And so basically what we're going to do then is we're going to use these circles to represent our rollers. And then eventually these circles will drive the actual roller position in the model. So basically what I'm going to do is I'm going to draw in my 7-inch power cell. I'm going to make it a construction line so that because it's just a representation of a model, so it doesn't actually need to be extruded or anything like that. That's kind of what construction lines are for. And then I'm going to give it a tangent constraint to the ground. So you'll notice in this case, the origin is on the edge of frame perimeter, and then it's on the ground. Right, and that's useful for us, or that's in a meaningful position for us, just because it kind of is a nice centralized location that's standardized for the intake. So when this ball is tangent to the ground, that means it's rolling along the ground, right? So now I can kind of look at my interactions and kind of position my rollers roughly, so that it can take in a ball from off the ground and then pull it up and over the bumpers. And then basically my next step is I'm going to assign some dimensions. These are kind of arbitrary, but I'm going to round them off just so I can start nailing down my roller positions. And then to move them around, I'll tweak these dimensions to give it the proper position I want. So I'm just going to assign these dimensions, 11.75, sure. So it's kind of arbitrary just based on where I place them, and I'm rounding it off to a nice round number, just because having crazy decimals doesn't really make a whole lot of sense while modeling. And then we'll come back and we'll accurately position them. And then you'll notice that I'm adding these dimensions, oh, not that dimension. And then you'll notice that all these dimensions are in increments of like a 1/2 inch or a 1/4 inch. And that's just to keep a nice round number on things. Okay, cool. So now I'm going to make another circle. So just a Control-C, Control-V, sketch copy. And then I'll make them equal instead, just so we can get rid of that additional 7-inch dimension because we already have a 7-inch ball. So now we can kind of see when the ball rolls in along the ground. So this roller will engage it, pull it in, and then it will get pushed up against the bumper and it'll get popped up and kind of dragged up into frame, right? So now we're going to fine tune our interaction so that there aren't dead zones. Like here you can see that a ball could theoretically get stuck here because it's not touching any roller or the bumper. So we just want to move things in a little bit and fine tune that interaction. So I'm just going to decrease this by 1/8 inch and see what that does for us. Okay, I think we want this one to come in and down a little bit more. So I'm just going to make this 7.5 minus 0.125. So I'm just going to tweak these numbers a little bit to kind of bring in and fine tune my roller positions. Looking at the starting roller, this one's kind of important because that's obviously what starts or pulls the ball in the first place. So I think we do want to move this up a little bit. Oh, that's not up, 6.625. There we go. Maybe 6.75 inches. Sure. So now you can see that it can pull the ball in, and then you'll notice obviously that there is some interference there. And that's because you do need your roller to interfere, actually. I just realized I forgot to set my roller sizes. That's not good. That's kind of important. Yeah, so our rollers in this case will be 1.25 inches, just because we're going to use the Versa roller system. Yes, and I'm talking too quickly. That's just fine. Okay. Yeah, so we can see that the ball is going to roll in and then get pulled in. Though making that roller did actually make it smaller, which is important, right? So now I need to move these in a little bit more. So maybe 9.25 there, probably a bit more actually. Let's try 9 inches, sure. Okay, so we can see it's going to come in. There is going to be a tiny dead zone, it looks like here, though I think that's kind of necessary at this point, just because it is kind of a min-max between the roller compression here and here, as opposed to the minimum compression point, which is right here, right? But hopefully the ball should have momentum as it's going through, so it shouldn't really get stuck in that momentary dead zone. And the other thing to note too, when thinking about stuff like this, is that there is flex in the intake, so it is able to like pop up, for example, because everything isn't exactly rigid, right? So that's just kind of a consideration we have to make while designing something like an intake mechanism. And the other thing to note too is we can build a prototype of this and kind of like if this is during the actual season, we would probably build a prototype of this just to figure out, or just like look at all the interactions and make sure they were good before finally building the final mechanism. And then based on that prototype, we could figure out, you know, if we need to tweak any of these numbers or make any changes like that. Let's see here, so 14.25 inches, sure. So you can see it'll get popped up and then passed off to that one, and then that will push it out into the actual robot. Maybe a little bit lower than that one, 14.125. Sure, I think that looks pretty reasonable, right? So I'm just being careful to watch. Minimum compression always occurs when the ball is passing between rollers, and then maximum compression always occurs in between the roller and the plate, right? So you can see maximum compression is here, and here, and here, and then here as well, right? So I'm just double checking. And the other thing you might see people do is they'll dimension balls in, and they'll like draw them in. And that way, and then what you can do is you can use a German dimension in that case to actually get a readout of your compression. So that can be a faster, or that can be an easy way to quickly see all of your compressions at once. The downside of that is it kind of clutters up your sketch with a lot of balls. That can be a way of doing it as well. Though we'll just do the faster way of just holding a ball in place and kind of eyeballing it for today, because this isn't the most precise thing we're doing right now. Okay, so I think that looks pretty reasonable, so we'll go ahead and finish the sketch. So now we have a sketch laying out of 3 roller positions, which is pretty good. So the next aspect we're going to look at is getting it in and out of frame, right? So in order to do that, what I'm going to do is I'm going to create a copy of these rollers, preserving the relationships in between them. So what I did was I just connected the centers of each of these circles with lines, right? And you'll notice I've started a new sketch as well, just to keep our sketches nice and simple. So then what I'm going to do is I'm going to create another set of these rollers, and they will be equal to each other. And then I will also do an equals constraint from here to one of these rollers so that all of these rollers are now the same size. And the benefit of that is if I change a roller in this size, so I'll also update in this sketch.
Oh, that's big brain.
Yeah, so that's pretty useful. Let's see here. And then what I'm going to do is I'm going to connect these sketches in the same way. And then by using equals constraints, I can make this triangle here that I'm drawing now. Oh, not what I wanted. And then once again, using construction mode to toggle construction lines because these lines aren't actual modeling elements. But then I'm going to make each of these lines equal to their corresponding element. And so what that does is it makes these two triangles congruent to each other through triangle congruence, which is something you probably learned about in geometry and then forgot. But it's side, side, side congruence. Oh boy, heart attack, geometry, exciting, flashbacks. But yeah, so that's kind of how that works. So the next element we're going to represent is we're going to do a 4-bar. So basically the way this 4-bar works is there's a pivot point back here for each of these 2 bars. You can see, and each of these pivots connects to the middle of the roller, right? So they're double using the pivot point essentially. So we can represent that by using some lines like this, right? And actually they don't have the same endpoint. But notably, these also connect to the intake when it's in the up position, right? So we have an intake when it's in the down position, we have an intake in the up position. And you can see how these arms will pivot between them. And because the arms aren't changing length as it pivots up and down, we can go ahead and we can make these lines equal to each other because the arms are constant, right? So now what we can do is we can constrain our intake to the position we want when it's in frame, right? So I'm just going to assign some dimensions here. We want our intake roller to be back a little bit, so a nervous judge doesn't disqualify us because that would be unfortunate. So 1.5 inches back from frame will do for now, just so we have a little bit of safety clearance. And then I'm actually going to constrain these endpoints because that's kind of important for mounting. So we'll do 8.25, sure. And then we'll go back as well. And then you'll notice I'm being careful to use my default planes as opposed to like this line from the bumper sketch. And the reason for that is because the origin planes are always robust, right? No matter what happens to the model, no matter what changes, these 3 planes will always exist. Whereas something could happen to this bumper sketch, for example. Maybe someone, fat fingers and decides to delete it. Maybe you decide to change it for some reason. So it is feasible that this could change, that this bumper sketch could get changed or deleted in some way, whereas these origin planes will never go away. So it's always best to reference these when you can, especially when it's a choice between choosing like here and here. It's the same reference, but this one is perfectly robust. Yeah, go ahead.
When would you suggest using more planes?
Yeah, so construction planes are useful when you want to position model geometry in different positions, right? In this case, we're just drawing on the right plane because that's the plane we care about, or that's the plane that's useful to us. But actually, I think we will move this geometry to represent the side of the intake we want, right? So right now we're drawing in the middle of the intake because we're going to make the intake centered on the origin. But I think what we'll actually do is we'll move the plate, the sketches to be on the side, right? So we'll actually do that now. But yeah, so here you can see the 4-bar interaction. So you can see our intake in the down position, our intake in the up position, and these bars will traverse between them, which is cool. Once we make them, actually. Okay, yeah, so now I'm going to make a construction plane to represent our intake off to the side. Actually, before I do that, so one thing I'm going to use for this variable, or for this design in particular, is I'm going to make a variable. It's going to be type any. So the reason why I'm using a variable is because I can use these values elsewhere in the design, and if I change this value, it will update, right? So you'll notice that I made this variable a number variable, not any. So it's a number that's 25, right? You could use a length here, like 25 inches, and you would get the same effect, though sometimes it breaks for some expressions just because of the way Onshape handles units. So it's just a little bit more consistent for us to do 25.
Wait, Alex, did it just go like 25 times bigger?
No, it did not. I just assigned this variable, but I'm not actually using it anywhere yet.
Wait, what does it do then?
Yeah, so I can use, so variables can be used anywhere throughout the part studio, right? So in this case, I'm going to use it for this plane because I want this plane to be offset half of the width of the intake, right? So I just did hashtag intake width using that variable divided by 2. So now this plane is 12.5 inches off of the origin. And if I change this variable, then the plane will automatically update. So something that's important to note while using variables is they're a very useful tool, but you kind of want to keep in mind, oh, I need this plane to be up. So you notice I tried to change this plane position, and I tried to move it to this plane, but I couldn't. And the reason for that is the plane was underneath it in the model tree. With the way modeling works, the load order, with the way the model order works, elements load from top to bottom. So if you edit an element in the middle of your tree, you won't be able to select things that are underneath it. So you see in this case, all of my sketch 3 geometry disappears when I edit the sketch. And that's because sketch 3 is underneath sketch 1 in the model tree. So that's an important aspect to note. So like if I want to put the sketch onto plane 1 has to be above it, because otherwise plane 1 hasn't loaded in yet when you're actually editing sketch 1. So I'm just going to go through quickly now and move my sketches onto plane 1, just so that they're off, kind of in their proper position in space. Okay, cool. Let's see here. What else do we have to do now? Looking at my notes. Okay, so we're going to keep sketching here. So now I'm going to make another sketch. So just trying to keep my sketches nice and simple, because making sketches is pretty easy. You can always reference other sketches. So now I want to draw in these two standoffs here that kind of run across and connect the plates together. So I'm just going to do a little triangle to represent it. This is kind of arbitrary, but I'm just kind of doing it this way because it's how I want to do it. I see that's almost 2 inches, so I'll just round that off. And then this triangle will be our position. And I'll just give it an angle and a position so they're fixed in place. And we can always come back and edit these later, right? So I'll just do, how do I want to do this? Sure, I'll just give it a somewhat arbitrary angle here, 120 degrees, sure. That looks pretty reasonable. And then we can always come back and change it later. Actually, I'll dimension this number instead, just because this is a little bit more meaningful, because we want it to be close to the roller, but not too close. Okay, sure. That looks pretty reasonable. Okay, what else do we have to figure out? Oh, okay, I'm just going to add a point here to represent our motor position. So eventually there will be a motor on this arm here. So you can see that there's actually a belt run that's powering the intake that runs back to the motor, which is mounted back here. So I'm just dropping in a point to represent the motor. And then we'll use that when we're actually creating our plates later on. Okay, let's see here. Anything else we want to add? I think that is everything. So now we will go ahead and make our plates. So I'm going to use a plate feature script I designed to actually generate my plates. So basically the way this works is you select your exterior geometry, and then you can go back and add in holes and other pieces of geometry you want later on. So I'm going to choose my outer geometry, and then I'm going to go through and add my holes. So I'll start out with a bearing hole. So this middle piece of geometry will be a bearing hole. And then we'll have a smaller bearing hole in the front and back for these smaller bearings, whereas this middle one is a bigger bearing, just because the hex shaft needs to run all the way through it. So we can transfer power through it. And then in the back, we'll have a 0.196. So these would be our standoff holes. So that's our intake plate. Oh, positioning, let me remember that. So I'll give it a plate thickness of 3/16 of an inch. 3/16 of an inch is just polycarb, which is the same material the cheesy poofs use. But it's a very flexible material, which is good for us, because that way if it gets hit, it won't shatter. It'll just bounce and flex back. And then we can see, I like where this is. Okay, cool. So now I'm going to create another construction plane, just offset 3/16 of an inch from this first one. And the reason why I'm doing that is just so that our plates aren't right up against each other, so there's room for like the flanges and things like that to fit between them. Okay, yep, so there's our plate. So now I'm going to make our arm plates. So once again, we'll do point, point, point. Oh, I forgot something actually, hold on. So actually one trait we want is we want these plates to touch when they're down. So I'm just going to go ahead and represent that relationship with a line. So I'm just going to throw a line into the sketch and kind of constrain it somewhat arbitrarily, perhaps. Let's see here. We'll just do this, like this, so something like that. I'm just going to use these construction lines to get the distances. So I'm just going to make this equal and this equal. And we'll do it like that. Oh, okay. How do I want to do this then? Let's go ahead and make, how do I do this? In this length. What does that do for us? Oh, that's right. So what I'm going to do is I want this line to be kind of in between these two lines, even though they're not parallel. So what I'm actually going to do is I'm going to use a symmetric constraint to constrain this line in particular. And then we don't need the length. That broke it. Why did that break it?
Why? Why did it break?
Excellent question, James. Let's delete some constraints real quick and see what that does. Okay. Curious. Oh, maybe we only need one set of lines. So we'll just do like this and like this. Obviously, this isn't the most scientific way to organize it, but I think it'll serve us for our purposes. Actually, it's curious that that broke because I have a feeling this is going to work now. No, it's not. That's weird. It worked before. It's saying it can't solve it. Okay, maybe we can do the length then and get away with that. Hi, Jake. We're currently in the middle of designing an intake. Just as kind of an example. So we've done some sketching, and now we're going through and making the plates. Okay, so now I can make our plates. Now that I have that line in position. So I'm going to go through the same process. So I want this hole, this hole, this hole, and this line here. And then we'll add our motor. So this will be a 550 type motor. We don't need the vent hole, and we'll just toss it on here. And then for angle reference, we'll have it point towards this. And then for holes, we'll have a 0.375 inch hole in the back here for the pivot. And then up front, we'll have a bearing hole. So this will be 1.125 inches. Okay, so that's our lower plate. And then now I'll make our, oh.
You say 0.275, it looks like it input 3.
Oh, did it? Oh, sorry. Yeah, I meant to say 0.375, which is 3/8 of an inch. So that's just a little bit bigger than like the standard size we have. So we can do like a bushing and then like a 1/4 inch shoulder bolt, which is kind of like a standard mounting scheme. We'll talk more about that in the future. Don't worry too much about the specifics of it right now, I would say. And I'll just assign the plate plane as this. And then, so that way we have our gap. Nice. Okay. And now I'll make our other plate. So you notice that when I use that sketch in a plate, it hid. So I just have to reactivate it so I can once again select it. So just making it unhidden. And then I'm just going to drop in my geometry like this. 0.875 inches for this hole here.
Alex, we have a question in the chat.
Yes.
Luke asked, what about the belt distances?
Yes, so we will need to do that next.
Yeah, that's very important.
Yes. So for those of you who aren't familiar with belts, typically the way you tension belts, or like ensure that the belt is properly tensioned so that it's not too loose or too tight, right? So that way you can actually put it on, is you calculate the center to center distance of the belt, and then compute it that way, right? So basically when you do that, you need the distance between the belts to be very precise, because it's a function of the pulleys you're using and the belt teeth you're using. So actually what we're going to use for that is we're going to use my belt calculator to actually add in our belt runs. So here we go. So we're going to make a belt run between this point and this point. Did I do this right? No, I did not. Hang on a second. So I'm actually going to flip my plates around so that my sketches are on the inside. And the reason why I'm doing that is it's just that way my sketches are in between, so that my intake width is from the inside plate to the inside plate. So that way if I decide to change my plate width later, it won't affect that, basically. And now, do I need to, oh, I think I need to increase my offset a little bit more. So I'll just flip this plate 2. I forgot to update this plate thickness as well. That's fun. And then I will increase this offset just another 3/16 of an inch. So we'll make it 6/16 of an inch total. And that's just so we still have that proper distance we want. This plate is not correct the way this is. Plate thickness flip, please. Thank you. Awesome. Okay. Yes, so now we'll go through and we'll do our belts. So I'll choose offset from pulley 1, even though we don't have it modeled in yet, so it won't.
Oh, hold on. Where did you get this belt?
I made it myself.
Oh, frick. Whoa.
Yeah, so this is a custom pulley generator I created over the summer that will allow us, or that will be useful for us. So have it automatically choose the best belt size. So we can see here it's giving us a 115 tooth belt with a 5.196 center distance. So now I'm just going to go back and update my center distance in my sketch. So I have to redo some, so I have to change some constraining around, right? So that we can actually enter that 5.196 because this will break. So I'm just going to delete one of these dimensions. So we can't constrain it in all axes like we had originally. So this is going to affect some of our geometry a little bit, but hopefully it won't affect it too much, right? Okay, cool. So that's that. And then the belt calculator actually automatically checks if the center distance is correct. And if it is, then it becomes happy. So here we can see that it's happy, so that means we entered it correctly, which is cool.
Alex, are you currently just copying over the exact same design off of one of the major FRC teams?
Possibly, a little bit. Steal from the best, innovate the rest is a great adage. So I'm just going to make another custom belt run here, 30. So I'm doing it 30 to 24, so there's a little bit of a reduction. If you look closely, you can see that this pulley is bigger than this pulley, and it's the same thing here. And the reason for that is so that way this intake roller will spin slower than this intake roller, which will spin slower than this intake roller. So basically, as the balls are going through, the rollers will accelerate them. So to actually get separation between the balls, which is a desirable trait. Because that way balls coming in won't hit balls that are already in the intake or that are in the process of being intaked. Let's see here, offset from pulley 1. So this offset needs to be, I cheated a little bit and wrote this down before, but it needs to be 25 minus 0.65 inches, just so that's in the right place on the other side of it. Actually, we can use our hashtag intake width again here. So we'll do it like that. And then I'll have it auto choose the belt size again. So we can see it's giving us a 110 tooth belt, and the center distance is a nice 4.9 inches, which is great. So I'll just go back into my sketch here and add that dimension as well. Okie dokie. So there we have our intake and our belt. And then we have one more belt run to add, which will go along this plate here. So I'll do that now. Oh, that's the Onshape official one. That one's nice, but it doesn't have all of the FRC specific features mine has. Yeah. Okay, so we'll just position it using the sketch points again. Let's see here, pulley 1 is our, actually, I'll have pulley 1 be this, and pulley 2 be here. Just that way I can offset off of pulley 1, which would be nicer for us. And then pulley 1 will be a 48 tooth custom pulley, and pulley 2 will be a 12 tooth, so we won't add that pulley in now. Technically, this is violating general Onshape practices because we're creating multiple copies of the same custom pulley in a part studio, which you probably shouldn't do because it will mess up the bill of materials essentially. So the way you would get around that is you just not add pulleys on one of these belt runs, and then the assembly, you could assemble it again. Yes. So we'll do the auto choose belt thing again and see which belt we get. Where did our belt run go? Oh, there it is. Okay, and then I'll just set my offset up now. So we want this to be 3/16 of an inch. a little more.
Wait, how are you setting the offset? Is that on every single like thing that you can make?
No.
Is that what that measurement is?
I designed this in myself. Or well, yeah. Basically while I was designing it, I wanted to have an offset. And so that's what this is here. Unlimited power. Anyway, okay, there we go. So that looks right. And we can measure it to see what we want our center distance to be. But here you'll notice again that it's unhappy, it's red, because the center distance is incorrect. And the great thing about this too is if the center distance were to change inadvertently down the line, maybe you fat finger it while entering it, maybe you forget that it's an important dimension and you delete it for some reason, it will turn red if it's incorrect and warn you that your center distance is wrong.
Alex, is this an advertisement for your FeatureScript? Are we gonna have to pay for it in a few years?
No, it's already available to the public. It's actually linked in my presentation that's attached to this, or that I have with this. You can find the link to all my FeatureScripts, including these two today. Okay, cool. So there we have our plates. So now we're just going to do some miscellaneous work. So basically what I'm going to do is I'm going to assign names to my parts, just so that they have somewhat meaningful names. So we'll call this one the intake side plate. And we'll call this the intake. Oh, this is the intake. We'll call this the intake lower arm. And we'll call this the intake upper arm. Okay. And then I will assign properties and materials. Materials is important because that way you get appropriate weights. So you can figure out if a robot's going to be too heavy ahead of time, which is always nice to have. Polycarbonate, and then I will also assign appearance. Appearance is less important, but it looks nice, which is always fun. And because it's polycarb, we'll give it a reflection value of 0.33. Sure, that looks pretty good. So that looks like polycarb, more or less. And then normally you would assign any other parts you have as well, but we don't have to because the belt FeatureScript assigns the parts automatically, or the weights and appearances automatically for us. So now I'm just going to do one last thing. I'm going to make a standoff running across. So because there's two standoffs and they're both the same, we'll only model in one in the part studio, and then we'll just assemble it again in the actual model itself. So I'll just turn on this model so I can get this. I will offset a little bit. This is Ricky's custom length FeatureScript, or custom length extrusions FeatureScript. Very useful for extrusions. So we will grab a standard extrusion. Just a round unthreaded spacer. I don't think we'd actually use this if we were actually doing this, but it's a demo, so that's okay. And then our length, we'll use our variable width again. Right. So you notice that we used our variable 3 times in this part studio, which is good. Generally, anytime you have a variable, you want to be sure that you're actually using it a few times, because otherwise it kind of defeats the purpose. And it looks like this isn't actually in the right spot. Let me double check that real quick. Minus 0.625, that should be correct. Unless we're not offsetting it correctly. That's curious. Oh, I forgot to offset my spacer, that's why. Or I offset it in the wrong direction. Or actually, I'm not supposed to offset it, that's right. Okay, there we go. So there's a round unthreaded spacer. And then we'll call this the intake spacer. Sure, why not? It doesn't have to be like the best name in the world, it just has to be somewhat recognizable. And I'll assign the material, so this will be aluminum, just so we can have weight, which is nice. Sorry, 6061 aluminum. There's different types of aluminum. 6061 is the most common, though it is kind of expensive, so I don't know if we actually use it all the time or not. Okay, so that is the part studio stuff done. So as you probably noticed, we only have half of an intake. We could mirror across our stuff if we really wanted to. but we will try to avoid that today, just because we don't actually want duplicate parts in the Part Studio. So rather than like making this part twice in the Part Studio, we will make it once and then we will assemble it twice. So that way we have two copies of one part instead of two parts that are the same part. So hopefully that distinction makes some sense to you.
Are you saying that we put it into an assembly after this?
Yeah, so we're going to put it into the assembly twice, rather than putting two copies of the same part into the assembly. Yeah.
If
Can you
you so
explain why
wanted
that's so
to.
useful to do that versus?
Yeah. Honestly, it's kind of the same. The biggest reason is it helps with like workplace management. Because you have like two copies of the same part, then like someone might get confused or like not understand the distinction, and then suddenly you have, you know, 2 or 4 copies of the same part that you don't need, and you're like, well, now what? And also it just helps with the bill of materials particularly. So you actually can like get the bill of materials and it's correct, and you can order everything nicely. So only unique parts in the Part Studio. I kind of broke that rule today, but we don't talk about it. Okay, so insertion. So there's 2 ways to insert parts. You can either insert an entire Part Studio at once by clicking this, or you can get specific parts by clicking the dropdown. Actually, we don't want this one. We want this one because this is the one we just used. I have another Part Studio in this document because I made this intake earlier, just to double check everything's the same. So I'm just going to insert everything at once by clicking here. Otherwise, you could get individual elements. And if we were to like add other parts and then come back and add them, we wouldn't want to insert the entire Part Studio again. So we want to open the dropdown and then find the part we actually want to add. And then you notice I can come out here and drag it around, but I don't want to actually do that. So I'm going to use the green check mark instead of coming out here and dragging it. Because you notice when I mouse over the menu, it snaps into place. And so every time it snaps into place, that's it snapping into the default position. So when it's in the default position, the origin of these parts is the same in the assembly as it is in the Part Studio. And that is good because it helps us keep our origin in a meaningful place. And it's, yeah, that's a good thing normally. So here you can see our origin is, you know, behind the intake on the ground, and it's in the same place in the assembly. So now in order to keep it there, what we're going to do is we're going to fix one part. So I'm going to right click and choose fix. And then because these parts are inserted in the default position from a Part Studio, we can actually group them to constrain them very quickly. Yes. Let's see here. And then actually, yeah, and then I can go ahead and insert the additional copies of the parts I need. So now we're just going to insert another intake lower arm and an upper arm and another side plate somewhere over here, and then we'll insert another copy of the spacer because there's 2 of them. So now we have 2 copies of the same part rather than having 2 parts that are the same. They're copies of one another. Yeah, so now we're just going to do some basic fastening work. So just going to call down a fasten here. And then I will use, so this green check mark finishes the fasten and then finishes it. If you choose this one, it will finish the current mate and then start a new one. So I'll choose that because I'm doing a bunch of fastens in a row. And then I'm actually going to use this standoff here to constrain it. So that way, if we change the length of the assembly, it will, the standoff will change, which will move this plate for us. So it will stay current as well. So then actually what I'm going to do is I'm going to move some of these parts into a new subassembly. So that way we have a subassembly with just the intake rollers and kind of the fixed elements. And then we have another assembly, and then the top level assembly will have the bars and things like that, just to keep everything nice and consistent. So I'm going ahead and choose the components that I want to move, not that belt run, pulleys, hum-de-dum, pulley 1, that pulley, that pulley, that pulley. And then we'll choose this and the spacers, and then we'll leave the arms, not that arm. Yes. Okay, yes, that's what we want. So then I can right click and choose move to new subassembly, and that will do that for us. So you notice it just created a new assembly down here, and it moved all of those parts into an assembly in this part, and it also broke some things. Because it tried to move some of the constraints over, but not all of them. So now I have to assemble this constraint in the exact same way. So one part is already fixed. And since some of these parts are in the same place as the part studio, I can group those parts. But not all of them, because like this spacer in particular is fastened in place rather than being from the part studio, so I can't group it to constrain it properly. Or I could group it, but it would be bad. And it wouldn't have like the robust behavior we want. Yes, so I'm just going to make a group constraint here. Yep, that's good. And then we seem to have lost our side plate, so I'll just insert another one. Because it's not too bad. Where did it go? Here it is. I'm blind. And we'll just fasten it in place real quick. Okay, coolio. So that's that for now. So now we have our assembly here. And then we won't actually fix this in this assembly, right? Or actually we will. That's right, because that's fixed in that assembly, but not this one. Is that right? Can I unfix this? I can. Okay. There we go. Okay, cool. Yeah, so that's that. So now these parts are, some of these parts are unconstrained. So now actually what I'm going to do is, because these parts are locked relative to each other, I can actually use a group constraint for that, even though they move relative to this part and the rest of the assembly. So I'm just going to make a quick group of this plane, and I'll call it develop run, just so that's a little bit clearer what it is exactly. Okay, let's see here. That's the plate fastened. We already have the plate in from the assembly, so we can just delete this one. Just because I missed it while moving the stuff to a new subassembly. Okay, let's see here. What do we want to do next? Let's see, what time is it? It's almost 6. Okay. Okay, so let's quickly go through and do some pneumatic geometry. So just looking at how the intake's actually going to get in and out of frame. And then we'll do some more assembly, and then I think that will be it for this mechanism. Maybe we'll also do the rollers. I don't know. That shouldn't be too bad. Okay, so I'm just going to do a quick sketch. So basically the way pneumatics work is they have a set stroke. So usually you buy them by the stroke, so like 3 inches, 4 inches, 5 inches, depending on what you're choosing. You can also get like super stroke ones with like an 1/8 inch or something like that have a crazy amount of power. Those are called pancake pneumatics. But when you're thinking about strokes...
Wait. Is it called pancake pneumatics?
Yeah, it's like a pancake cylinder. So those usually have a stroke of like an 1/8 inch or less, and they're very powerful, typically. Very fun. Okay, so basically what happens is you have a mounting point on your plate, and you have another mounting point. So we have our plate drawn in, or we have our plate represented in 2 positions, right? So this line represents our plate when it's down, and then this plate represents our plate when it's up, right? And so basically what that means is this angle here should be equal to this angle, right? Because if you think about where it's mounted on the plate, it's staying constant, right? And so we can represent that using a triangle where this length is our stroke length. So in this case, we'll just do a 4-inch pneumatic, just because that's kind of the pneumatic I'm familiar with. Let's see here. So then we want this angle to be the same. And actually, I'm going to get a little bit lazy today and just make it coincident with this. Though you could have it like floating out here, for example. I'm just doing this to save a little bit of constraining time because we are running a little bit up low in time, perhaps. Okay, yeah. So this would work here, right? So our pneumatic, when it's extended, would have our plate down, and then when it's retracted, it would have our plate up, right? So then the rest of our pneumatic would be out here, represented by this line. And I'll use B for parallel. That's the keyboard shortcut for the parallel constraint. Why is that? It's because P is reserved for planes. Poo-poo. Yeah, I can press P and you can see I can toggle all the planes on and off at once. So then this length here would be the distance between the pivot point of the pneumatic and the double clevis when it's retracted, right? So I don't actually know what that distance is right now, so I'm just going to use 8.5 inches for now. And then eventually I could come back and update that to be what I wanted. Actually, that's not great when it's like that. Fine. Okay, I won't be lazy. So I'm just going to delete these constraints to free this up. Basically, we need this angle to be the same as this angle. It's kind of hard to get dimensions to be the same in Onshape. So we're going to have to do some shenanigans with triangle congruency and constraints to get this to be proper. Don't worry too much about this part of it. Okay, I'm struggling. You probably won't have to do this, or like if you do during the season, I'll be there to help you through it. Basically, I'm just going to create some lines that are a known parameter, just so I can make these two triangles congruent. I'm sure there's a better way of doing this, but I'm not really sure what that is right now, which is unfortunate. That's okay. Okay, let's see here. Constraining. This should be 4 inches. We'll use an equals constraint for that, and an equals constraint here. And then
I'm confused. Didn't we just make them tangent to the line?
Yes. Well, basically, I need this angle here to be the same as this angle, which isn't actually that easy to constrain. It's a little weird. But yes. Let's see here. How can I do this? Oh man, I had this done earlier. I'm having flashbacks. Let's see here. Oh, okay, I think we want this line here to be represented. So that this can be equal to this. There we go. So now if we make these equal, theoretically, that should constrain our triangle, and indeed it does. Okay, great. And I'll just make these construction lines because this is kind of a construction element. Okay, so then, yeah, so now you can see you can kind of mount it wherever. And so this is how you can kind of control your pivot point for your pneumatic. So just kind of pick an arbitrary position today. I'll just do this angle for now. Sure, 170, why not? But later on, you could come back and like give one constraint to this if you wanted to have it in a specific position, for example. So now I'm going to roll back down to the bottom of this. And then I'm just going to add this hole to my plate. So I'm just going to add it to the exterior geometry. You do have to select the exterior geometry in order. Fortunately, I chose this point last and this point first. So I can just click it. And then I will add the hole. Sure, it can be, we'll just do another 0.375 inch hole. So that's right here. Wait, no, it's this one. Okay, there we go. So that's added into our plate. And then actually what I'm going to do is I'm just going to make a short example plate to connect them. So that way we can mount our assembly plate in the model. So I'm just going to pop up another plate feature script, hum-de-dum. Go kind of fast. Pop, pop, pop. We'll add some holes. We'll make them 0.375 inches. And we'll do something like that. 3/16 inch plate. Okay, sure, banana plate. And then I won't give it a name because I'm just because we're running out of time here. We're not really running out of time, but I don't know. We'll assign the material though. Polycarbonate, done, and we'll make it. Oh shoot, that's not what I want. We will edit the appearance. Okay, white and 0.33. Thank you. Okay, there we go, banana plate. So now I can go ahead and insert this into my Part Studio. So I'm going to use this drop down, insert it in the default position, so not dragging it around, but just leaving it there. And then I will actually fix this part into position because I haven't fixed the part in this Part Studio yet. And I didn't want to fix one of these arms because they need to rotate. So now to get my intake movement, I can use Revolute Constraints so that these can spin freely. So I'm just going to select these mate connectors here.
Wait, did we just fix that to that? or nah?
We are doing revolute constraints. So this arm can spin about this point, but it's constrained on the axis, so these holes will always line up. Does that make sense? Okay. Yeah, so I'm just going through and adding revolute constraints because if you think about it, all of these joints will be able to spin freely, so they all need to be represented by revolute constraints. And then for the other side, I might get a little bit lazy with planars, but we'll see. Offset, -3/16 of an inch. Okay, let's see here. So that should do that, and then I'll just do the other side as well. I think we'll get lazy for this. -3/16. Did I enter that right? No, I did. Okay. Ah, yes, the joys of design. Okay, there we go. Yes, so to recap what we've done, right? So we've inserted these plates, and these are fixed with revolute constraints. And then this plate is fixed in position. This assembly is actually free floating, though it is constrained by the 2 revolute constraints we added. So now we can see, if we go to rotate this, we can actually see the movement of our intake, which is pretty cool. And then to get these arms to sync up with these ones, I'm just going to use a planar mate, so that, because the arms should be parallel theoretically. So I'll just drop this here and drop this here. What? That's not supposed to happen. Okay, never mind that for now. Let's add our intake rollers real quick. So for this, we'll be using the Versa Versa roller system, just because I'm familiar with that. We probably wouldn't actually use that during the season, but maybe we would. But there are some configurable parts that will allow us to add that today. So if I go over to assemblies, I can go ahead and add in my rollers. Let's see here, 24.5 for the bottom one. I took some notes on this process earlier, because it's a little bit finicky getting the right dimensions. And then, so anytime you're inserting a configurable part, you want to click Generate, which updates this, and then you can click this to actually insert it. If you don't click Generate before clicking up here, then it won't actually update, and you'll get like the default configuration. So I'm just going to go through and insert all of my rollers. So we want another one that is 24.25 inches long, with 0.875 inch shaft on both sides. Be done, and then we want just the tube, because adding the hex shafts in is a little bit, or this configuration can't handle the hex shafts basically. So we would normally add those later. Though we probably won't do that today just because of time, and because adding hex shafts is pretty boring. Yeah, so those are the rollers, and now we can go ahead and fasten them in place.
Wait, but Alex, how do we oh, was it to that thing?
Yeah, and you'll notice that that only one part of the assembly moved. The reason why it's done is just for performance reasons. So you want to move the rest of the assembly, you can click Solve. And that's something that happens every time you try fastening an assembly, no matter what you're really doing. And then you'll notice I'm fastening these in place rather than like using like a Revolute mate or something like that. And the main reason for that is just because performance. Because seeing your roller spin isn't that useful in terms of like understanding your design. And Onshape can use all the help it can get basically. So there's not really a great reason to make all of your rollers spin. Though I do know several designers who like doing that. And if you do like doing that, more power to you. But it's just not something I typically worry about too much.
They can be safe in the knowledge that the roller can indeed spin.
Yes. and then it won't hit anything while doing so. I don't know. If you have like an interference you're worried about, or like something that might be a little bit close, then you certainly can. Otherwise, it's probably not the most worthwhile thing to do. Why is this too short? Ooh, 0.188. Okay. I appear to have shorted this one a little bit. That's weird. Where is it? Configuration. That's weird. I'll just add on our 0.25 inches, and we'll make this touch. So I won't have an offset on this one. Just standard design fare, basically. Adjusting offsets, things like that. Dum-de-dum. Okay, and then we'll do this one the same way, kind of. But this one actually, the bearing goes in the outer hole, so we'll actually offset it 6/16 of an inch. We'll flip it around. Oh, sorry. -6/16 of an inch. Okay, there we go. So that's like that. Why is that wrong? Did I mess something up?
Okay, so hear me out, like really quickly, sorry to interrupt, but I'm in the middle of doing pass-offs, so
that's fine.
Yeah, Miss Harrison's on my butt about it, and I'm literally having to spend pretty much until 7 doing these. Okay. So I'm not going to be able to hop on. I'm just saying hi for the moment before Miss Harrison comes back.
That's all right.
Just know that I would have come if I didn't have to do pass-offs.
Yeah, it happens. It happens.
This is a recording?
See you guys.
Yeah. All right. That'll just be in the recording. That's fine. Okay.
Out with like a photo, like with a video editor or something. That's what I do.
It's an option too. I don't know. It's fine. It's not a big deal. I'm just.
Wait, are we gonna edit out Carlos?
Wait. Why is this wrong? Unfortunate. Okay. Sure, good enough. Or we'll measure it and short it. Now it's triggering my OCD, so I want it to be right, even though it probably doesn't matter the most. What is this length that you reduced by? 0.5. Okay, great. No. Anyways, but yeah, so we're kind of wrapping it up more or less. There's still a few more things to figure out, but at this point the design's mostly complete, right? So hopefully that was kind of a good overview of the design process. So typically we start out with sketching, and then go through and do some of our other modeling, things like that. Did I mess that up in some way? No, okay, trick of the eyes. But yeah, let's see here, how does that work? Okay, so I can actually insert our other banana. I'll just go ahead and finish this design off because we're almost done. Obviously, you'd also probably want to add bearings and things like that because we're missing a few of them, and like hex shafts. Ooh, the motors, those are also kind of important. But we won't do that today for time's sake. But that wouldn't be too difficult normally. Usually the hardest part about doing bearings is just figuring out which way you want to go with that other direction. -25. Okay, coolio. So that's fastened in place now, and then it's just a few more Revolute mates. Lots of Revolute mates on this one. This one goes in the front. Set -3/16. Yes, that looks correct. One more Revolute. Okay, there we go. So there we can see our assembly is fully proper. And then yeah, so we can see the full range of motion, and we can see that it does indeed get in frame, which is good. Always useful when you are actually allowed to compete because you didn't mess up your design. But yeah, so that's pretty much it. I think that's everything. Oh, the motor. Let's add the motor. That's kind of important too. So that's pretty simple. It's just, we'll just add a motor from MKCAD. And my voice is dying. This is fine. Assemblies, Neo 550, and we'll do a 12-tooth GT2 pinion. So just go ahead and insert that. And then I will fasten it in place. So I'll grab the face of it, and I'll grab the middle hole, and then I will slap it on our motor mount. And then you notice it's the wrong direction, so I can just use the flip primary axis to face it the right way. And then when I click done, it should give me the solve if I click the wrong one. Yeah, so there you can see the pinion. I don't think this pinion is the most accurate because it probably would be out a little bit further. So the belt's clipping it right now, but that should be fine in the final product. But yeah, so that's it. That's our intake. Oh yeah, so this one has a 12 to 48 reduction on the Neo 550. I actually did, I made a JVN calculator, which is a design calculator we use to look at gear ratios. Because basically you have to figure out, like how fast do you want your rollers to be spinning and things like that. So you can trade off the speed of your rollers versus like the amount of torque they can output. Because obviously you could like spin them super fast, but then you probably wouldn't be able to actually intake anything, or it would jam really easily, just because they have like no force. It's kind of the trade-off you have to look at. But yeah, that's pretty much everything. So yeah, and then here's the assembly process again. So you always want to insert one copy of any parts from Part Studios into their default position, like I did, and then you want to fix one part in place, and then you can create a group constraint to automatically constrain any Part Studio parts that you have that are in the same place in the assembly as they are in the Part Studio. And then that will create that robust reference that we like. And then I have the design resources in the presentation. You can also check out the sketching documentation slideshow I made if you want to learn more about sketching constraints and all the tools in the sketching involved with sketching. Yeah, so you can see we actually did quite a bit of sketching. Oh, and yeah, something to note about this design is because we use sketches, we use them to generate all of our parts and things. If I were to change any of these sketches, it would automatically update the entire model. So maybe we decide we want to have our pivot point back a little bit more and maybe a little bit higher. So you can see that that adjusted our geometry, and then that also went ahead and resized our plates and things. And that also changed our up position, for example. So you can kind of see the ripple effect it has on the model and how everything is propagating and robust in the way we like. Yeah, so do we have any questions then, or is that kind of it? Yeah.
Thank you, Alex.
Okay. Yeah.
Also don't look at the chat.
Okay, I'll stop the recording.